Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective, and this is lecture number 54 where we continue our study of 3-5 material and their role in high speed devices. So, let us again recapitulate what we learned from our initial slides and then we will go step by step into the generation of high speed devices. The first of all, that one major characteristics of compound semiconductor devices are its high speed operation. So, basically because of its high electron mobility, which is about 5 to 6 times larger as compared to that of silicon, you can operate that at a very high speed. High speed basically means that its switching speeds are relatively high, right? And since the switching speeds are relatively high, you can also able to generate high frequency signals in the output, right? And and therefore, it has been seen that unlike silicon, gallium arsenides or gallium nitride can be used for all high frequency or microwave applications because its current does not reduce at those high frequency level and your power levels are relatively very high. Then if you want to, you can also use these devices for low power, but then the stress on the devices will be relatively smaller. Then sometimes these devices are also used in for light emission purposes, for example lasers and LEDs. That is the overall characteristics of a semiconductor device. Sometimes you will see that they are also used as photodetectors, right? Photodetector basically means that once to detect light of a particular wavelength, right? And therefore, the concept is that if you have this band gap available here, right? This is the band gap. Let us suppose this is the conduction band, and this is the valence band. And then, how do you detect a light? Is basically that that whenever a light falls, right, and its lambda, which is hc by lambda, is the energy carried by that particular light, becomes almost equals to the or greater than the band gap of this material, you will have these electron hole pair formation taking place. And if you have an voltage or an electric field available within the device itself, these electron hole pairs moves in the opposite direction, and as a result a current is formed, and from there you can detect that a light has been falling onto the material. However, if the energy which is being propagated by the light is smaller than the wide bandgap material, then it will be just converted into heat and the lattice will also increase its heats. If it is more than the band gap, it can go to the top of the band gap, much higher on the conduction band. It can release its energy in a thermal fashion and sits at the bottom of the conduction band, right? So that such that the total energy loss is approximately equals to the lattice energy loss plus the band gap which is available to us. So, this is how you are actually detecting light in a photo detector, right? And you can do that very easily otherwise. How is it done technically, or in an actual, you can actually use a PN junction to do that photo detection. If you have this depletion region here, then depletion region will be exactly equal on the both the sides. When you fall light onto the system, the depletion region will be devoid of any free charge carriers, but because of light falling onto this depletion region, they will be suddenly having a large amount of electron hole pair generation. Because of strong electric field within the depletion region, these electron hole pairs will be shifting on this side and this side, and thereby a spike of current will be formed. When a spike of current is formed, you know what type of or what is the energy which has come out. This is the concept of photo detection in semiconductor, and 3.5 does it in a much better manner. In most of the sensor application, if you look at the second point here, in sensor application also compound semiconductors are used, which is sensitive to magnetism. However, 3.5 are also sort of resistance against nuclear radiation, ionizing radiation and heat, right. So, these are some of the positive points of compound semiconductor. What are the not so negative, but economically not a viable process, because compound semiconductors are relatively much, I should say, much costly in terms of fabrication process flow, right? So it's not so your return of investments are questioned when you typically work in this domain, but nonetheless it has got its own very fixed advantages as compared to your silicon devices, right? And that's the basic advantage of fundamental principles of the compound semiconductor. So it has got various roles, I told to you already earlier, but one area where people have been also working to a larger extent is basically in the domain of optoelectronics, right, where you study the application of electronic devices with interaction of that with respect to light. So, as you can see on the right hand side, the graph here, that when the optics meets with electronics, that is the region where we define as optoelectronics. All LED, display, laser diodes, solar cells typically require these compound semiconductors in a detailed manner, because that's application domain is very specific in that case. Now, what are the various other applications? We'll quickly go through it. You can find it other literatures which support it in a much better manner. And with the rise of 5G, the compound semiconductors are used, for example, gallium nitride and indium phosphide for powering 5G infrastructure. So, all your power amplifier design, which were traditionally silicon based semiconductor in high frequency environment, are being replaced by gallium nitride and indium phosphide, which can handle not only high power, but can also handle high power is one of the advantages, but it can also handle high frequency applications. So, high frequency application and high power application, both advantages are there for indium phosphide and gallium nitride. With the advent of I think electric vehicles, both domestically as well as in international markets, compound semiconductors like silicon carbide sort of is an ideal material for EV application, because it can withstand high voltages and temperatures, right? And they are also used for power converters. Because of requirement of high end IoT devices and sensors, high performance sensors and RF components are also being used by for 3-5 semiconductors. Now, let's come to the other application area. Um, One area which is coming up, if not in a very big manner, but it is coming up nonetheless, is that quantum computing area. Why? Because most of your sensing application for quantum computing is typically done on microwave scale, and that's where compound semiconductor comes into picture, right? And therefore, they are fundamentally used to detect the qubit, quantum qubit, right? And the information carried by the qubit through a microwave, they are detected, and that's where gallium arsenide is used in a big manner. We've already discussed quite a lot on gallium nitride and silicon carbide used in consumer electronics, especially in basically electric vehicle and so on and so forth. In energy efficiency and sustainability, solar energy happens to be one of the application areas where it is used to a larger extent. And what people are also working, a group of researchers are working on integrating these 3-5 materials on renewable power energy systems. Since you are actually miniaturizing the semiconductor devices, because that's the way to move forward in order to put in more application per unit area of silicon or 3-5, it is used for high frequency and high power applications, as I discussed with you, and this is used in medical devices, aerospace engineering and wearable technology. However, one important not a drawback but challenge is how to integrate a 3-5 with, say, silicon based materials, right? And that's the one of the major sort of a challenge which semiconductor devices face as far as 3-5 semiconductors are concerned. Okay, let me now come to the materials and the role in high speed devices. What we will do is we will look into the evolution of transistor technology, and then we will go ahead with the objectives. For example, we will start with inversion type indium gallium arsenide MOSFETs and HEMTs. We will look into the integration of 3,5 semiconductor on silicon, HEMT, and then look into basic GaN based HEMT, energy band diagram, microwave transistors, and applications of HEMT. Okay, I think this we have already dealt with you earlier, so I will quickly go through it what I've shown here on this PowerPoint on this presentation slide. If you look at the planar MOSFET, as I discussed with you, it's very simple. It is planar, which means that it is on the 2D plane in which you are actually trying to find the current here. If you, which is the first, this is a plain transistor. However, if you go to FinFETs and Tri-Gate FETs, since it is above the 2D plane, we define that to be as a FinFET at a Tri-Gate. And then if you have 3D plane, sort of a gate all around, then we define that to be as a nanowire FET. Now, as I discussed with you, this attention is now being also a substantial group of researchers in academia, industry, and everywhere in various labs are turning their attention to 3,5 semiconductors to replace silicon, as I discussed with you in a previous lecture as well. Now, and that is to do with high electron mobility, which I have pointed out here, and higher IDVG for 3,5 at the same gate voltage, which means that if you use the same voltage, you get a much higher MOSFET current. If you look at the left hand side graph here on the ID versus VG graph on the left hand side here, then if you plot the drain current ID versus gate voltage here, then you see that the red one, the red colored one which you see, right, is for TFETs, is basically tunnel field effect transistor whose subthreshold slopes are relatively very low, and it is even smaller than 60 millivolt per decade, very good switch. However, its on currents are relatively small, as you can see, it's tapering out in a sense as it goes to high values of ID. If you look at the green one, which is this one, silicon MOSFET, then its on currents are also relative. Please understand, this is a log scale on the x axis. So, the difference which you see is physically small is actually very large when you convert that in the linear scale, right, and it will be relatively much larger in that case. So, let us compare the green with the blue one. If you look at the green and the blue one, you will see that its subthreshold slopes are almost the same. Around 60 millivolt per decade is what is the subthreshold slope for a 3,5 MOSFET and a silicon MOSFET. However, 3,5 MOSFET has got much larger current handling capacity as compared to silicon MOSFET, as it can be seen from this graph. First thing. The second thing is that, however, we can show it from this graph that the VDD for silicon is larger as compared to VDD for 3,5 for the same amount of current to flow, which means that if I draw a straight line here for the same current, if you look at the 3,5 MOSFET, it has got much lesser voltage as compared to silicon MOSFET, right. And if you look at 3,5, 3,5 has got a larger one as compared to that of TFET. So, if we go for the amount of current we want to flow, basically, then VDD TFET is smaller as compared to 3,5 as compared to silicon planar MOSFET, right, in terms of the amount of current carrying capability being exactly the same in all the cases. Look at also the graph here and see that if you extrapolate this green and blue curve backwards, then my I of, which is available to me, the off current is when the gate voltage is 0, the amount of current flowing through the device is off current. The off current is relatively higher for 3,5 material as compared to silicon silicon MOSFET. Now, you will ask me why is it like that? There are certain reasons for that, but which means that the off-state power dissipation for silicon MOSFET is relatively much higher as compared to that of 3,5 MOS device, right. Let us now come to the mobility part, the right hand side. If you look at the mobility part here, and on the y axis we have the basically injection velocity in the order of 10 to the power 7 centimeter per second versus the gate length effective gate length. Now, as the gate length goes on increasing, the velocity will obviously going on decreasing, because since electric field will reduce for the increasing value of your gate length, and when the electric field reduces, the saturation velocity, the velocity also decreases. But if you look at one by one, if we compare, so this whole lot here you see, this is for indium arsenide, and we have got compound and tertiary compound indium gallium, Indian gallium arsenide of various mole fractions available to us, right? And if you look interestingly, as you move ahead and you have indium arsenide, if you look, it has got an extremely large value of mobility of 13,000 centimeters square per volt second. If you look at 3,5 material, then it's basically indium gallium arsenide with gallium mole fraction of 0.3. The blue colored curve is having a mobility of 11,000 centimeter square plus volt second, and that of gallium with a mole fraction of 0.47 has got a mobility of 9,500 centimeter square per volt second, right? Which means that as you move from uh, a, a dual compound indium arsenide to a triple compound, which is three element compound, then we see that the mobility starts to fall down as you move ahead, right? That, which means that as you move from indium arsenide to indium gallium arsenide, it falls down. Not only that, if your indium mole fraction drops down and your gallium mole fraction increases by the same amount, we also see that the mobility actually falls down, which means that it is also to do with in increasing the gallium component from 0.3 to 0.47 or reducing indium from 0.7 to 0.53, you will see that there is a change in the value of the mobility available to you. So, now a lot of study has been done for last many decades, where we do have the knowledge about how the mobility behaves with respect to the channel length and as well as with respect to the compound semiconductor dimensions. However, let us look at the last curve here, which is a very low, and that is silicon, strained silicon, right? Strained silicon has even lower value of of injection velocity as compared to that of compound semiconductors, right? And so these are the various, just a sort of a feedback or a sort of an entry level feedback to you in terms of both silicon as well as for gallium arsenide, and comparing that with indium gallium arsenide as a tertiary compound. Okay. With this, let's look at the inversion type of MOSFET and HEMT. And the inversion type of MOSFET and HEMT are is shown in the left hand side. How do you integrate it currently? What we have seen, and people have reported across the world, experimented and reported, that indium gallium arsenide MOSFETs have got the highest GM, which is obtained in the case of HEMT. Let me just refresh your memory. GM is basically your del ID VGS, right? And that is the highest value which generally you get out of it, right? Now, if you look at the left hand side graph here and the right hand side graph, we will go one by one. And if you look at the left hand side graph, it is basically plotting GM on the y axis, right? GM on the y axis with respect to the year of, when I say year, it basically means the manufacturing year. It's relatively old data, but typically stands good nowadays even. If you compare an indium gallium HEMT with that of indium gallium arsenide MOSFET, the transconductance of almost being equal, but slightly it has been achieved much earlier as compared to that of indium gallium arsenide MOSFET, right? And therefore, indium gallium arsenide HEMTs have got a rate of change of current is much larger in that case, and it is relatively high. Whereas, if you go back to the right hand side figure, which is this one, then if you plot R on resistance of the device with respect to the year, it has actually started to fall down. However, an interesting part which is happening is that the gallium arsenide MOSFET shows a much drastic fall in the value of your on resistance as compared to this thing. One major problem area of HEMT technology is that it suffers from relatively high sort of a gate leakage current, right? It has got a relatively a high gate leakage current. Now, this is uh, uh, how you place or integrate a 3,5 semiconductor on silicon, and the direct wafer bonding technique of thin 3,5 layer, for example in this case indium gallium arsenide and soy is being used. So if you look at this first one, I have this silicon, right? I have this silicon here. This is the native silicon which is available to us, and then you put a buffering layer so that you don't allow any heavy materials or any other material to destroy your silicon. So you grow a buffer layer, and over that buffer layer you grow an indium gallium arsenide, this thing, and this is basically a epitaxial growth, which you get, right? Once you have it, and then you what you do is that you just rotate it, and then you rotate this one to the top, and then you place it over the box. So box is basically barium oxide, right? So if you very well look at it, this is the box layer which you see. We have an indium aluminum arsenide and indium gallium arsenide, and then you have a high K material being generated here. So this is basically a methodology of a 3,5 material on silicon being formulated, right? Now, the technique used is basically heteroepitaxy. Using a thick buffer layer is applied to achieve a high quality 3,5 layer. How will you generate very well defined 3,5 layer on silicon substrate, right? And that is what shown here in this case. Now, the indium gallium arsenide, which you have already grown n type, is then transferred into the target silicon wafer and bonded on the barium oxide part, right? And then the bonding wafer is released and then can be reused for growth. So this happens to be sort of a seed device which can be used for multiple number of times when you want to integrate this device with others one. Now you see that typically the mature HEMT technology, which you will see, the high electron mobility transistor technology, will have a relatively low leakage currents, right? Will have relatively low leakage currents available to us, and that is primarily because you are able to sustain a much better interface qualities in this case. Whereas, so if you look at the development of silicon, the development of silicon technology has the advantage of, you remember we have already discussed this time and again, that silicon has got an advantage of having a native silicon dioxide growth being available to it. The native oxides of 3,5 material easily result in what is known as a Fermi level pinning, right? And thus the gate is unable to perform a very well defined uh, 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 current flow because the Fermi level pinning takes place, right? That is the reason why 3,5 MOSFETs have not made good progress for a long amount of time, because of the pinning, and you don't get enough free electrons available to you to participate in the current flow. Now, many unpinning Fermi level methodologies have been formulated, and one of them is GD203 on gallium arsenide. So, people use, for example, GD203 on gallium arsenide, right? They use typically that, and tremendous progress have been made to improve the interface between 3,5 material and silicon in order to have a much better profile of the bonding material. Another important breakthrough which has happened is by introducing what is known as an atomic layer deposition, right, ALD, and this is to fabricate a decent quality gate stack on gallium arsenide. So if you have a gallium arsenide here, you can form a relatively good quantity of gate stack here by doing what is known as an atomic layer deposition, but many performance issues in terms of optimization the process for the best output is still being worked out to a larger extent. Now, if you look at the schematic of the aspect ratio trapping technique, which means that the before and after the 3,5 layer, right? Before and after the 3,5 layer has been grown. Now, if you look at the 3,5 layer itself, this is the right, on the left hand side you have the silicon, and you have a native silicon dioxide being formed as sort of a uh, uh, hill over silicon, and then you try to etch or try to grow a 3,5 material within these small etching is there. But when you do that, you basically end up having a very high dislocation and stacking fault because of the growth mismatch between 3,5 material and silicon, right? And the sidewall becomes very strained sidewall, and therefore, though your top level is typically good quality 3,5, but your sidewalls are relatively bad 3,5 sort of layers of materials available. Now, if you look at the schematic of the fully grown 3,5 nanowire on silicon, so this is a GAA device, gate all around device, and on the left hand side, if you look, is basically what is known as a vapor liquid solid VLS technique, right? And this is the VLS technique where you grow the 3,5 material around the oxide layer here, and you have this native silicon being generated here, and on the and if you want to grow a nanowire, then on the right hand side, 3,5 nanowire, what is known as selective area epitaxy, SAE. So you don't have to do an epitaxy on the whole area. Only in those areas where you want to effectively grow the 3,5 semiconductor, you can grow it using a nanowire selective area epitaxy. On the right hand side, you can see the nanowire TEM image available to you. There is another methodology where you what is known as a template assisted growth technique, right? Here, very well and well defined thin nanowires can be grown, right? And people are using these techniques for growing very thin aluminum wire. On the right hand side, if you see, is a simulated image for that. We have the silicon substrate here over which you grow indium arsenide. So this is your indium arsenide, and then you have the silicon dioxide, which is the buffer layer, and this is the silicon layer which I was talking about. So if you go back to this diagram here, right, this diagram here, you will see that the same structure which you see here can be actually replicated to a larger extent by at this particular point, right? And this is very standard technique which is being used, and a very effective technique which has been used for silicon. Okay, so with this, let me stop today's lecture here and let me recapitulate what we learned. We learned the basic, maybe I didn't go into details of how the growth structure will be, but at least we learned the various techniques available to grow 3,5 semiconductor, compound semiconductor on silicon, so that we are able to at least have a basic understanding of the structural properties of compound semiconductor. In the next turn, we will take up high electron mobility transistor and its fabrication. Thank you for your patient hearing.